So I would like to talk a little bit about a new type of spectroscopy that you're going to be using in part 3 of this week's copper complex analysis lab. So you'll be using what's known as UV-Vis, or ultraviolet visible spectroscopy, to perform the analysis for copper in this complex. So we've talked about one type of spectroscopy before, that was photoelectron spectroscopy. Spectroscopy, in the most general sense, is the study of interactions between matter and electromagnetic radiation. We're using light to learn something about the atoms and molecules in our sample. So, in the most general sense, whatever spectrometer or instrument you're working with is going to be monitoring which wavelengths are absorbed by a substance and which are not, to learn about some property of that sample. What you can learn depends upon the wavelength or the region of the electromagnetic spectrum that you are exposing your sample to. Different regions cause different things to happen within your sample. So if you are exposing your sample to microwave radiation, this will generally increase the rotational energy of molecules, which can give us some information about molecular structure and geometry according to how they enter or how they absorb that microwave energy and enter higher energy rotational modes. Infrared radiation causes bonds to vibrate at different frequencies or in different ways, entering different vibrational modes, and this allows us to detect the presence of specific types of bonds within our sample. For instance, you can tell, is there a carbon-oxygen double bond in my sample? Is there an oxygen-hydrogen single bond in my sample? That is all information that you can get from an infrared spectrometer. Visible and ultraviolet light is what you're going to be using in the lab. Causes electrons to be promoted to higher energy orbitals or into an excited state, which allows us to detect the presence of certain substances as well as their concentration. So by looking at the UV-Vis spectrum, you can sometimes identify what is present in your sample, or tell its concentration if you know what the substance is. So UV-Vis, or ultraviolet visible spectroscopy, is the one that we're going to be using, measures how much light of a given wavelength is absorbed by a sample. So you can collect data about absorbance at all wavelengths, which is the plot that you see to the right here. Shows you wavelength on the x-axis, absorbance on the y-axis. So the higher this line goes, the more photons of that color are being absorbed. So you can see that we have a pretty low absorbance in the blue and purple, and it increases as we move up towards red. So you can collect data like this, and this can help you identify a substance if you don't know what it is, by where the peak lies, and the shape of it as well. Or what you're going to be doing in the lab is collecting values for a single wavelength. So you're going to see how one wavelength changes, moves up or down in absorbance with different concentrations. So when you're studying absorbance at a single wavelength, you usually want to use the wavelength of maximum absorbance, lambda max, or at least one that is relatively high. So when choosing a lambda max, usually you want to look at that graph that we were just looking at on the last slide and choose your wavelength from there. But you can also get some sense of what's going to be a reasonable wavelength based on the color of your substance. So the color that we perceive something to be is generally the color that is least absorbed by that substance. In order for you to see something as blue, blue photons have to reach your eyes. That means they were not absorbed by the sample. They either passed through it or bounced off of it, depending upon whether you're talking about something that's translucent or something that is opaque. So the sample that you're working with, the copper coordination complex, is blue, means that it has a very low absorbance in the blue region. So these wavelengths down here are not very highly absorbed, which means that something pretty far away from that, something very different, is likely to be a better choice for recording your absorbance, because those are going to be the wavelengths that are actually absorbed. The graph that you saw on the last slide is actually the absorbance graph for the compound that you're working with. So this is the absorbance over wavelengths 400 to 725-ish nanometers. of the copper coordination complex that you're trying to study. So we can see here that the absorbance in the blue and purple and green region is very, very low, which is why we see this as a blue color, because these are the photons that are actually making it to our eyes and being detected, whereas the red and orange and yellow are being absorbed into the copper atoms themselves and not actually making it into our eyes. So we have a much higher absorbance down this end of the spectrum at higher wavelengths. So that is where we're going to be recording. So you'll actually be recording absorbance information around, I forget the exact number, but around 650-ish, somewhere in here. It's not the maximum for us because copper's absorbance actually increases on into the infrared region a little bit. So we want to pick one that's high enough, but not too close to the limits of detection of our instrument, just because it gets a little bit less accurate as you get to those extreme wavelengths that are at the edge of what it's able to detect. So you're going to be using absorbance at a single wavelength to calculate the concentration. The absorbance of a sample is directly proportional to the concentration of the solution, as well as what's known as the molar absorptivity and the distance light travels through the solution. So this is known as the Lambert Law. It's shown to the right, A equals epsilon BC, where A is the absorbance, E is the molar absorptivity, B is the path length, and C is the concentration. Molar absorptivity is a constant for a species that describes the intensity with which it absorbs light of a particular wavelength. So the higher the molar absorptivity, the greater the percentage of photons of that particular wavelength are being absorbed by your substance. So we're working with copper 2 is the species that we're detecting by UV vis. So molar absorptivity will be constant for our experiment. The path length is just the distance that light travels through your sample, which is the width of your sample's container. So we use these special square test tubes, essentially, known as cuvettes, to do these types of experiments, and most of them, including ours, are 1 centimeter in width. So both molar absorptivity and path length are constant in most UV vis experiments, meaning that absorbance and concentration are the only things that change, and they're directly proportional to one another. So what you're going to be doing in the lab is first collecting enough data to calculate the molar absorptivity for copper 2, and then once you know that, you can use it to find the concentration of any sample. And that's how you're going to be able to determine how much copper is in the complex that you're analyzing to finish up your analysis and determine your empirical formula.